very much. Right, I might need a little bit of help from Sid with the tablet and going backwards and forwards. But today I'm going to talk about elements that are critical to your future. So I'm going to talk about strategic elements and critical materials. So these are some different elements that you haven't necessarily covered in your classes. So it's extending your range even further. Why they're critical to the sorts of things that we would like to do in everyday life, and what we can do to make sure that we've got a stable supply of them. So first of all, a little bit about the Birmingham Centre for Strategic Elements and Critical Materials, where I work.
The current world population of 7.3 billion is expected to reach 9.7 billion by 2050. Combined with a growing middle class in countries that are developing, this creates an ever-increasing demand for products, services, technology and energy. These all require strategic elements and critical materials. These elements and materials are crucial to our modern lives, underpinning clean energy technologies, automobility, aviation, modern electrical devices, the pharmaceutical industry, and a whole host of other everyday products and services. Previously, the UK has considered its critical materials strategy in the context of being part of the European Union. However, with the vote of Brexit, there is the need for the UK to develop policy to consider what resources are critical to the UK's industrial strategy and how it plans to meet the needs of UK manufacturing. The naturally occurring deposits of certain elements are not uniformly distributed around the globe. By way of example, deposits of lithium, which are used in batteries for electronic devices and electric vehicles, are primarily located in Chile and Australia. Niobium, which is essential to efficient aircraft engines, gas turbines and future fusion reactor technologies, is predominantly produced by Brazil. Platinum group metals, which are used in jewellery, fuel cells and as catalysts, are largely from South Africa and Russia. China has a dominant position in the supply of many light and heavy rare earth elements, as well as a wealth of other critical materials. Where materials are of key economic importance but at a risk of short supply, we need to consider other approaches to obtain these strategic elements and critical materials.
We will explore how to mitigate the impact of materials criticality through approaches such as substitution, regulation, reduction, and finally reuse through recovery, recycling and concepts such as urban mining and the development of entirely new industrial ecologies.
The Birmingham Centre for Strategic Elements and Critical Materials encompasses expertise from across the Birmingham Energy Institute in biosciences, chemical engineering, chemistry, earth and environmental sciences, economics, law, material science, physics and social science.
We're working on the development of new methods and new technologies to enable the recovery of critical elements from end-of-life materials, from wastes, from scraps, and even from road dusts.
We've developed novel technologies that allow us to recover very small concentrations of critical elements from wastes. One of the challenges that we face is recovering metals at concentrations as low as 5 parts per million.
We have previously developed advanced robotics methods for sorting and segregating dangerous nuclear waste, but we are now looking at how to transfer those technologies to automatic sorting of other kinds of complex waste streams in order to efficiently separate valuable materials for recycling.
We are looking at ways to reuse components containing strategic and critical elements and developing new processing techniques to use these materials more efficiently. For example, we have technology to recover neodymium rare earth magnets from computer hard drives, electric vehicle motors and wind turbines.
We are looking at how to produce nanoparticles for catalysis that reduce the quantity of critical materials used. The development of nanomaterials will be key to the development of next-generation polymer electrolyte fuel cells, photovoltaics and lithium-air battery technologies.
An important focus of the Centre is also on the substitution of either the technology or the critical elements contained within a wide range of products. For example, light-emitting diodes contain elements that can emit light when exposed to UV light, but these are often in short supply.
The University of Birmingham has significant research activity on strategic and critical elements across many disciplines. For example, recycling and efficient use of rare earth metals in magnets, replacement of lithium and cobalt in batteries, and efficient use and replacement of precious metals for catalysis and platinum group metals.
The problems encountered by strategic elements and critical materials are often driven by economic and political factors, and this draws on expertise from across the campus, including the business school, social science and law.
The Birmingham Energy Institute is a collaboration of about 100 researchers across the university working on everything from technology through to economics and business models. We work with a wider collaboration of the Energy Research Accelerator, that is 6 Midlands universities working on some of the national challenges that we have around energy with international partners like the Fraunhofer. The new Centre for Strategic Elements and Critical Materials comes at just the right moment. It's a fantastic initiative. It comes at a time when Birmingham City Council is wrestling with its own challenges around waste management. This is a fantastic opportunity for the centre to work with the city around solving those issues.
So, there's a couple of different things going on here. First of all, there's the science, and then the exciting thing is that this is stuff that's happening in our community in Birmingham. So, you've had an introduction there to what strategic elements and critical materials are. I'm going to pass some around. So, lithium you're familiar with in the elements that you've already studied, but there's some different things here. So this sample here is coltan. It talks about tantalum there, but also cobalt is really important for mobile phone batteries. And here is some rare earth, which is used to produce magnets. So if you want to pass those around and have a look. Now what I'd like is a really strong volunteer from the audience. This young lady here, come up out to the front. So, why are strategic elements and critical materials really important? If you think about your mobile phone and the tiny little speaker inside, you need a very strong magnet in order to make a very small speaker that can make a loud voice. So what I want you to do is I want you to stand here, face the audience and hold your arms out straight in front of you. Right, I'm going to ask you to hold this one in this hand. Now, the rules of the game are you've got to keep your arms straight, you can't bend your elbows, and all I want you to do is just push these two together so they touch each other. Straight ahead, no, straight ahead, don't muck about. Just push them so that they just touch each other. I thought you said you're really strong, come on, just so they line up, don't bend your elbows, straight like this. I'll tell you what, do you remember how competitive your dad was? Shall we let him have a go? He'll be able to do it, won't he? Well done. Okay, so come up to the front. Right, so arms straight, no bending the elbows. Right, bring these together, straight ahead, come on. You're a strong man. No, you can't slide them, you just got to go straight ahead.
I can't do it.
Okay. Yeah, come on, if anyone else wants to have a go. Right. These will be available at the end, but we'll do one more now. Right, okay, so you stand out, face everyone so that they can see. One in this arm, one in this arm. Come on, show her Dad how it's done. No, you can't bend your elbows, you've got to go straight ahead. I know, it's hard, isn't it? So, these are... Well done. Well done. So, these are... Yeah, go on, what were you going to say? Oh, do you know? No. These are really, really strong magnets. Really, really strong magnets. And that's what makes them unique, is the fact that they contain an element called neodymium, which is used in creating the incredibly strong magnets that we use in speakers, in headphones, in mobile phones, in offshore wind turbines, they can use tons of neodymium in massive generators, because it means that by having a really strong generator, they can take out the gearbox. And obviously, if you build a wind turbine out at sea, that is a massive advantage because you haven't got something to have to service and maintain. They're also used in electric vehicle motors. So Jaguar have got their new I-Pace electric vehicle that's going to be made in the Midlands. That's got neodymium as part of the motor. So anything from hand dryers to vacuum cleaners, anywhere where you require a really strong motor or really strong magnet, neodymium is critical. Now, one of the challenges, as you saw there, is that there's only so many places that you can get neodymium around the world. Similar strategic elements and critical material challenges are lithium. You know, we talk about lithium-ion batteries in your mobile phone. So it's not just the lithium, although it's obviously lithium that you're familiar with through your periodic tables. There's also cobalt, which in many ways is much more critical than the lithium. And the challenge is there's only a few places around the world where there are massive deposits of this material, and getting to that material is challenging, not just because of mining, but also sort of geopolitical concerns. Right, okay. So, in terms of the periodic table, obviously you've been looking towards the top of this, but there's many more elements, and the ones that are highlighted in the white, they're elements that are particularly problematic or challenging. And if you can remember from the video, the definition of a critical material is that it's economically important, so we need it for business and industry, but there's risks to the supply. And that could be because there aren't many places that supply it. It could be because of the supply chain, so someone has to dig it out the ground, someone else then has to refine it and turn it into a product. So these are the critical materials. Now, there we go. So here's a map, and on this map you can see some of the strategic elements and where they're located around the world. So we were talking about rare earths, and you've seen the rare earth magnets here located in China. Other things include platinum group metals, so you might be familiar with platinum from jewellery, from catalytic converters in cars. We saw some of the applications there. You know, Russia, big supplier of platinum group metals. Democratic Republic of Congo, and we're going to see a little bit of video later, is responsible for a lot of the world's cobalt supply. And cobalt is really critical in the production of lithium-ion batteries. Now, the challenges, obviously, within that country, there's challenges with the regime, but then there's also problems with how the cobalt's actually extracted, because you've got children that, because they haven't got school or other activities, are actually having to dig the cobalt out of the ground themselves in what they call artisanal mining. And obviously that's not a very good life, and there's all sorts of challenges and you know, sad problems there. So we need to think about responsible alternatives and what we can do, how we can use science to enable us to either recycle some of these elements and look after them when we've obtained them, or to be able to substitute them for different materials. So we can see that demand is increasing. People are getting more and more affluent, they've got more money to spend, not just in this country, but people all around the world. You know, there's a growing middle class around the world that has got disposable income to spend on products and services. There are now more mobile phones in the world than people. You know, that's a massive statistic. This is electric vehicles, and it shows you how quickly the growth of electric vehicles and the market for those is around the world. This is in Bolivia, and this is where the lithium from the lithium-ion batteries that's used in mobile phones, in laptops, in electric vehicles comes from. And this is a salt flat, and the miners dig beneath this salt flat and they extract this rich, briny water, which is then allowed to dry, and it's from that material that the lithium is extracted. And so you can see here, you know, these are salt miners that are loading this truck full of the lithium-rich salts. But the challenge is if you look along the river delta in the region where the lithium's mined from, because of the large amounts of water that are extracted and then evaporated for the lithium mining process, there's all sorts of problems here for agriculture where the water table is dropping and farmers that want to grow crops are having to bring water in from other areas to keep their crops alive. And I said it's going to happen any minute now. And so for this process where the lithium brine is then dried out to make these lithium-rich salts that can be extracted. So this is a challenge. You know, this is massive environmental impact to deliver the products and services that we're all used to and that we're all familiar with. So we need to be able to find alternatives to this. So if you dig lithium-rich ores out of the ground, it takes 250 tonnes of the raw ore to produce 1 tonne of lithium. If you use this brine from South America, you need 750 tonnes of brine to produce 1 tonne of lithium. Now, if we could work out a way to recycle batteries from mobile phones, electric vehicles, laptops efficiently, and we all did the right thing and took our batteries to the right place for disposal, it would only take 28 tonnes of used batteries to make the 1 tonne of lithium. So massive advantages here if we can get things right. Also, if you go from sort of raw materials, it takes 500,000 gallons of water to produce a tonne of lithium. So again, there's massive environmental impact associated with the extraction of that water. And also there's energy. So to make a 1 kilowatt hours worth of battery pack, you need to put 400 kilowatt hours worth of energy in to produce those batteries. Now, if we can capture some of this by saving the strategic elements and critical materials, so those elements that are on the periodic table, rather than just putting them in the bin and them ending up in a landfill, if we can recycle them or capture them at the end of their life and put them into new products and services, we can be a lot more efficient with energy and the way that we use resources. So we spoke a little bit about lithium-ion batteries. This is the mine in China where lots of the world's neodymium comes from. So that's the material in these magnets. These magnets are called neodymium iron boron magnets. So you're familiar from your periodic tables with the boron and the iron, because I've seen that you've done that there, but maybe not the neodymium. So this is this big rare earth mine in China. And this is a sort of Google satellite image looking down. This is called the Bayan-Obo mine. And, I mean, China is rich in the deposits of these materials, but also the way it's extracted does terrible damage to the earth. So they are literally spraying acid onto mountains so that the acid can dissolve out the materials that are in the mine, and they can then run and then they can be evaporated. So you can see these big ponds of tailings, which is all the stuff that's left over at the end. Have you got a question? Really, really far away. So this is like taken from space, from a satellite or something like that. So you can see here it says railroad tracks, and you can see this tiny little line that comes here. So that gives you an idea of the scale, that this is a railway line and we are, you know, very, very far away. Gentleman there.
So if you put that magnet into the wall and then you threw it at it, put other one at it, it would just go...
It would just bounce away because these are strong magnets that are repelling each other as opposed to attracting. If maybe you made it in a different way, it would attract.
You could try it.
Let's not, in case I damage them. So you've got this mine here in China, and you can see from space, you know, the massive impact that this is having as a scar on the planet, The acid then runs into rivers and streams and pollutes them. Also, when you extract rare earth elements, you also end up with a lot of radioactive elements come as well. So the poor people that have to work in these conditions are being exposed to all sorts of things. So some really pressing reasons to look at recycling magnets, batteries and other critical materials. And so at the university, we're working on processes to deal with these different types of materials. So this is lithium batteries from mobile phones. One way that we can recycle them is to shred them up and do different things there. The problem is with that, everything then gets mixed together. So we're looking at more efficient processes, maybe where we can separate all the different bits of the battery robotically and then turn them into new batteries.
Cobalt, mined by children's hands in dangerous and dirty conditions in the Democratic Republic of Congo, filmed by Sky News. Cobalt is one of 40 minerals that end up in smartphones, part of a bewilderingly complex global supply chain, from suppliers to smelters to factories, assembly lines. Finally, it ends up in our own hands. The clean, blank modernity of the digital revolution erases its grim origins.
What they need to be doing, and companies should be doing, is engaging with their suppliers to improve the conditions at the mine site, to remove children from the mines, so that mining really can be a source of growth and jobs instead of insecurity and child labour.
So, these are young kids that should be learning all about elements with Sid, and their first experience of all this is having to dig this out of the ground in really dangerous conditions. So this is why we need to work on the science and technology to enable recycling. And here's an example of recycling these magnets at the university in the city.
Yes, we'll find out shortly. Now, scientists in Birmingham have found a new way to recycle important metals found in almost every type of technology. Magnets made of rare earth metals are a vital part of everyday objects, from mobiles to computer hard drives. But most of the world's supply is found in China, so recycling isn't just greener, it would secure a new source of these essential materials. Our science correspondent David Gregory Kumar explains.
This is a time-lapse showing how you recycle a magnet made of rare earth metals. You just pump hydrogen gas across it and it simply dissolves into a powder. At the University of Birmingham, they want to do this on a commercial scale. And this piece of kit, complete with borrowed drum from a washing machine, is how they're going to do it.
The magnet reacts with the hydrogen, it expands as it does so, and the structure starts to break apart, but crucially it demagnetizes the material. And then when you spin the electronics, the powder drops out through the bottom of the vessel, and then you can liberate a clean fraction of powder. And that material we can then reprocess back into new magnets, which is what I'm holding here.
Reducing these super strong magnets to a non-magnetic powder is what's so clever here. It would be impossible to recycle these magnets using traditional methods. They'd just shatter and then stick to the metal inside the recycling machine. And this is the ideal candidate for this new recycling technology. It's a computer hard drive. Now, we already recycle about 100 million of these every year, mainly for metals like aluminium. But they also contain up to 25 grams of rare earth metals. So for the first time, we can start to get at that and recycle that too.
So, there you saw in the video, do you recognise the name of an element that came across there? What were they using to recycle the magnets? Hydrogen, yes. So you've seen hydrogen. The hydrogen reacts with these magnets to break them apart, and it changes their properties as it reacts from magnetic to non-magnetic. So the problem is when it's magnetic, if you wanted to crush it up or recycle it, it would just stick to everything and you couldn't actually get it out. But by using the element hydrogen, we can make it expand and turn into a dust that's non-magnetic, and we can recycle it. Now, this is just up the road. Do you know the big Asda and the KFC on the roundabout in Small Heath going off towards the Coventry Road, Tyseley? Okay, so this is the vision for Tyseley Energy Park, which is just over the other side from the Coventry Road. So it's on the KFC side. There's a company called Webster and Horsfall there that's a Birmingham company that I think has been around for something like 300 years. They made the first transatlantic cable in Birmingham that went underneath the sea. They've got some wonderful historical exhibits where their company is so old that it presented at the Great Exhibition in 1851, and they've got these beautiful hardwood cabinets with all sort of pictures of their products and their cables that were made at the time. But obviously the world is in transition, so where they used to make cables for lift shafts going down into mines and other applications, there are now countries that can make that type of cable cheaper, and in this country we aren't using cables for coal mines anymore, so they wanted a new vision for that site and for industry in Birmingham. And so this is something that the University of Birmingham has been working on to try and demonstrate lots of really new and exciting energy technologies on that site there. And one of the big things that's going to be there is a centre, the Advanced Materials Recycling Centre, that's going to look at the recovery of critical materials and strategic elements. And you can see here, this green line, there's actually a distribution infrastructure there for hydrogen, which you've seen on your periodic tables. So they're producing hydrogen using renewable electricity there from a process called electrolysis. That's going to be used to power buses that run between the airport and the city centre. It's going to be used to be able to recycle magnets. It's going to be used to store power. So lots of exciting science that's going on the doorstep here. And like, you're young at the moment, but if you keep studying science, if you think about what you want to do, go to university. There's exciting careers in STEM on the doorstep in Birmingham. Thank you very much.
If they take the hydrogen out of when they make powder and it's non-magnetic,
yeah.
they do that.
So they drive that off later on in the process by heating it up, magnetise the material and turn it into fresh magnets. And so there's different ways that they can do that, with sintering or by resin bonded magnets. So that's a bit like araldite, you know, the two-part glue that you put and you mix it together. So yeah, all sorts of things they can do. But they're looking at putting this capability in Birmingham to both extract and manufacture the magnets. So yeah, exciting new industry.
Any more questions?
Was that one from the young man there? No, just having a wave. Thank you very much.